Okay, thank you very much. Do you hear me well? Yeah. Thank you so much for sticking around until the last talk, and I should thank the organizers for the successful event. So I will be reporting on the reference that is written here, and Walter has set this stage for what I will be talking about. The only comment I'll give is probably the architecture he was proposing is not first time done by Vendetti et al. We wrote this paper with very, very similar structure months before. And it's a joint work with Behrouz Saperi, Ehsan Ranmanesh, and Mike Friedlander, all from 1Qubit. Mike is also a professor in UBC. Okay, so I'll just have one motivation slide, and you all probably know Jeff Hinton. So I took the citations, the Google Scholar citations he had, and I wanted to make a couple of points. So you see a couple of events happening here around 2006, 2007, and then there's like 2012-ish where citations of the deep learning stuff skyrocketed. People had been working on, deep learning for a really long time. Backpropagation existed from, 90s, 70s. Perceptron was proposed in 1960s. But really usage of, large deep neural networks didn't become a mainstream until this paper that is the famous ImageNet paper that they wrote, so Hinton and his students. And really the big difference between this and the things that they used to do before is that they implemented all of that deep neural network, the feed-forward and back propagation, on GPUs. And that let them use much larger neural networks and much larger data sets, and then they got really, really good results on ImageNet. But before that, people were working on models that were different from what deep neural networks look. In fact, this is actually a slide from Hinton in a NIPS 2007 workshop where he is complaining that backpropagation needs a lot of label data, it's slow, it gets stuck in poor local minima, and all of these are things that right now, if someone starts learning about machine learning, they would think that backpropagation is very well tailored for these types of problems. So the work that we want to do, or we are trying to do, is to ask the same question whether we can use quantum computers to do what GPUs did for deep learning in some sort of a model for machine learning. And obviously the model is perhaps has to be different from deep neural networks because backpropagation is very well suited to fit the puzzle between good hardware, good algorithm, and good training process. Okay, so between the time that I said, like the few years before GPUs and deep learning became very mainstream, people were working on things that were called probabilistic graphical models. So usually they are classified into directed and undirected nets. So the directed networks are things that you draw a directed edge inside a graph between cause and effect in a way. And undirected neural networks are things that look like Markov random fields, conditional random fields, restricted Boltzmann machines. How does that connect them to quantum computers is this really interesting theorem of Hammersley and Clifford that show that any Markov random field to any Markov random field, we can associate an energy function, and then the state of the Markov random field, the mixing of the Markov random field can be described by the Gibbs state associated to that energy function. And so that connects like this machine learning concept to something that we can speed up perhaps on a quantum computer. But nevertheless, even though people do a lot of deep learning these days, state of the art refers back to inspirations from energy-based models and Markov random fields a lot. For example, you might know of the great success of DeepMind in doing deep reinforcement learning, but papers that came after these and tried to improve on things that were the deficiencies of deep reinforcement learning, we're trying to use things like energy-based models and mix them into deep learning. So for example, deep reinforcement learning, it doesn't do very well when you have to create a stochastic policy. Usually it creates a good deterministic policy. If the agent has multiple objectives, it doesn't do well in them. If the environment is very stochastic, deep reinforcement learning is not working well there either. Okay, so Walter talked about this hybrid architecture, and that's the one that we also independently proposed and tried to use. So we have what we call leading deep neural networks and then trailing energy-based models. Now, that can be a fully visible Boltzmann machine, an RBM with hidden layers, some latent space or not. So one reason that this could be seen as a generalization of just deep neural networks is if you have played with, say, MNIST, usually the last layer of the deep learning, instead of the nonlinear activation function, you use something called softmax. And softmax is basically Gibbs sampling from a system where there's no interaction between any two nodes. And that makes it easy to, you just have to create exp of some number. So in a way, we're taking that softmax last layer and thickening it, and that's what we call thickening of the softmax. And so before going further, I'll just quickly say, so we tried this on a task that is called image tagging. So this data set has 25,000 images. It has 38 words in it. And the difference between image tagging and classification is that you have to assign all the correct tags. So you're not trying to associate one word to an image. You're, in a way, like it's the first step to auto captioning, for example. So we want to associate all the correct tags to the image. And the state of the art at the time that we were doing this was AlexNet. So we used AlexNet. We trained AlexNet. And then we used the trained AlexNet and then added to that a energy-based model with different type of loss functions. All of these functions are of the form that you can use Gibbs sampling to optimize them, to evaluate them. And so we see an improvement over the purely deep learning model. One thing that we tried, given the feedback we got, was what if you take that deep network and whatever number of nodes you're using inside your RBM, just add that as another fully connected layer. And we see that if we do that, the test error becomes even bigger than the training error. So we see signs of overfitting in that case. So it's good to try to train the deep neural network until it saturates. Then you can add a probabilistic graphical model and then train with a new loss function and think of the leading deep layers as a feature extractor, the same way that Walter was talking about. One thing that is useful here is that we don't have to, we could backpropagate from here all the way to here in the same round of backpropagation, but we don't have to. We can train the deep neural network separately, exchange every image with its large feature vector, and then just consider the feature vector over on the probabilistic graphical model. Okay, and just so you see like examples of what this task looks like. So for example, here there's like a drawing of a face, and you have to recognize that that's not people. But AlexNet thinks that there are people in that picture, and for example, with the smooth structure prediction model, you can remove that people. And this one is an example in which, like, adding these layers didn't improve. The first two are showing how you can improve the results you get for these images. Okay, so we have a situation with lots of these quantum machine learning papers, and the problem is lots of the things we can run, we can't prove scaling for, and then lots of the things that we have proof of scaling for, we can't run, and that's a problem. So for example, the examples of things we can prove scaling for and we can't run them, probably for a long time, are quantum machine learning algorithms that are based on the quantum algorithms for solving linear equations. So these are usually known as HHL-based algorithms. And, the resource estimations for doing quite small, but relevant linear systems is very, very large. You need things like 10 to the 8 logical qubits, and you need to be able to do in the order of 10 to the 29 gates on them. So that's extremely large. It's not, we don't pass NISC into being able to do this for a really, really long time. But nevertheless, if you assume that you can do HHL, then you can do principal component analysis, supervised learning, unsupervised learning. One problem with them is that you also need something that doesn't look like the way we think about circuits today, and that's called quantum RAMs. And so it's not clear whether we can even physically create quantum RAMs. There are other problems. For example, if you are trying to solve a problem about the classical world, then you have some classical big data. You have to convert that into quantum big data in a way, and that's another problem that probably will remove all the speed up you would get from the algorithm. Probably, for example, quantum recommender system is in the sweet spot of some of these shortcomings. Okay, so what are the things that we can run, or we will soon be able to run, and we can prove scaling for? So that's like all these variational quantum algorithms, variational quantum eigensolver, the classical quantum hybrid state preparation algorithms, and things like that. And the big problem with them is that there is a very challenging optimization problem that we are assuming will be solved classically. But if classical optimization was easy, then we wouldn't create quantum annealers. So there's a little bit of a loop here. So the way I see where this work sits is that it's trying to, make a step towards bridging the gap between these two types of works. So I talked about the numerical experiments. I just want to use the rest of my time in trying to come up with proof of scaling in a way for these types, for the algorithm that we were running. So I will use the structured prediction problem as my main example. So as I said, the difference between structured prediction and classification is that you have exponentially many labels. So you can't, for example, just use a deep neural network with exponentially output nodes and then try to classify. So you need to use more sophisticated classification algorithms. Nevertheless, it's very useful. So in natural language processing, when you're trying to find cool references inside a sentence, image tagging that I talked about, image segmentation, recommender system itself, all of these can be formulated as structured prediction problems. Okay, so in structured prediction, the objective function we have depends on a continuous variable W. And there is a discrete set of variables that represent the labels. We will call them Y. For every training sample, we have an index I, and then Fi is the amount of uncertainty we have about the labels we associated to that image. So we want to basically take the worst badness of the labels we associated to all the training images, all the training samples, and then we want to minimize that. We want to minimize the worst uncertainty. And so that gives you a min-max, where the min is over a continuous set of variables. You can set this up so that it's a convex problem, but the max is over a discrete set, and that's the hard problem. Okay, so how does this relate to Gibbs sampling? So if I replace this max with the soft max, which is the log sum exp over the variables, which are Fi here, then I get the Boltzmann distribution over the values of Fi. And then the other nice thing about it is that if I want to find derivatives with respect to the continuous variable, then I just have to find certain observables, certain diagonalized observables of the Hamiltonian that represents the Gibbs state of that energy function. So in a picture, what happens is I have this W, and this term is like a regularizer, which makes each of these little dotted lines be strongly convex. And then I have to maximize the worst. So over every choice of W, I take the worst, which is the max, and then I have to minimize over that and then find this point. Now, the problem is, as you see those peaks that happen when I'm changing from one choice of labels to another one, those are places where if you try to run gradient descent, just on the left of that optimal solution, you have very large gradients pushing you forward. And then on the right hand of it, you have very negative gradients pushing you backwards, and that doesn't let you converge, and you wouldn't be able to recognize that this is what's happening. So the nice thing about finding a smooth approximation of this, say with a Gibbs distribution, is that when you're getting close to the local minimum, the gradient is also getting small, so your optimizer can realize to try to converge there. But of course, when you use a more aggressive smoothing, then you will get a bigger shift in the optimal in your approximation of the optimal solution. So you have to correct for that. Okay, so stochastic gradient descent is really bad for these problems. So it's like that one up there. And the reason it's not good is because it's correct, but the assumption is that you have unbiased estimates of the gradients, but that's not enough for what you need. You also need to reduce the variance of the gradients. And so what more sophisticated stochastic gradient algorithms do is that they try to do some sort of averaging over gradients, and that will create what's called variance reduction in gradients. So there are two techniques. One is that you create what I talked about, that you take your non-smooth convex function, you create a smooth approximation of it, and then you try to solve the smooth approximation with things that look like, stochastic average gradient descent, or you try something like a weighted averaging of the gradients, and this is called stochastic gradient descent with what's called polynomial decay averaging. So both of these have provable optimal convergence for the same problem. Okay, so now I'll tell you a little bit about how we prove what is the result and how we prove it. So Saga itself, what it does is that it has a list of previously evaluated gradients. And then what you do is that in every round of training, you pick a new sample, you calculate the gradient for that one and replace it for that index inside your table. And then when you take the gradient, you take the average from the updated table. Now, all the red parts are what happens if you don't have the exact gradient. So every gradient is plus a noise. When you remove the noisy gradient with another noisy gradient, then you get another vector of noise added to the average you have, and then your update has a noise. So the question we want to answer is, how can we, what is the control we need over the noise so that it doesn't blow up and it still converges? And so the model, we had to come up with a model for the noise. And the way we did that is we looked at, circuit model algorithms for quantum Gibbs sampling. So the way they control the noise is linearly dependent on the solution you have. So you get your estimate of the observable plus some additive noise, and the complexity of the circuit is inverse linear dependent on that. So I won't use this result, I won't use this complexity, I'm just trying to motivate the model for the noisy Gibbs sampler we used. So we assume that there is an additive error, and then we get inside that additive error with high probability. And of course there's one other technical detail that is, both the observable is diagonalized and the Hamiltonian is diagonalized, and both of them are bounded in norm, which are fine with, in our case, for example, in a structure prediction. Okay, so with this, the result is that you only need to do logarithmically many noisy gradient approximations, which is like logarithmically many times you have to use dviv, for example. And then the rest of the classical optimization runs with the approximate saga. To do that, you need to have the error be in the linearly dependent on the precision you want to get, which, you probably can't do better than that, given that the noise is additive. And so the only thing I want to say about the proof is that inside the proof, you end up having to use things like strong convexity and Lipschitz continuous gradients, which is the case when the Fazio, Bach, and we're proposing saga itself. But we also have to, you can't have a strongly convex function with Lipschitz gradients unless it's bounded, because if it is strongly convex, then the gradients will try to blow up. So we had to confine ourselves to a convex domain, and that actually is important inside the training of the structure prediction model. The last thing I want to say is that it's optimal, it's optimal in the sense that you can't get better than logarithmic dependence, and if you try to solve the original problem, you have to correct for that shift that I was talking about, if you do that, then you get almost optimal scaling for the original problem. So you get linear plus a log, but if you neglect the log, it's optimal. I will skip this part, which is about using this mode that is the complete optimizer and not the Gibbs sampler. It's a little more complicated, but we also managed to show that if you have an optimizer that with some probability give you the answer and with some probability completely fails, with same conditions, you can again converge with optimal scaling. You don't need to use the Lipschitz continuous gradients anymore, which is probably useful for more complicated tasks. And again, this is as well optimal. So I will conclude. So what I tried to do is to show that hybrid models where you use leading deep learning and trailing energy-based models is perhaps useful. We showed the scaling of them. We showed numerically that they work for complicated tasks that are known to be complicated. They're not toy problems. The scaling for average gradient descent techniques is near optimal for them, where scaling means the number of calls to, say, a quantum annealer. You can use it in a sampler mode or use it in an optimizer mode, and for both of them, we have theorems to prove this. And probably the outlook is, so one question that I don't know the answer of is whether these are good models for noise on a quantum annealer. So having additive noise as a Gibbs sampler or something like quantum minimum finding algorithm, is that a good model for the noisy gradients you would receive from quantum annealing? The other thing is to try to use this for more complicated problems and larger tasks. So with that, I thank you for your attention.
Oh, thank you. Nice talk. So, two quick questions. Are you saying that you can replace, for example, Adam with Saga for training deep networks, or?
You mean Saga with Adam?
Yeah, is Saga like a replacement for Adam optimizer for?
So Adam is numerically more efficient because it doesn't have to keep a table of gradients.
Yeah.
So Saga is like a theoretically good optimizer. If you can run Saga, then it's doing something like what second order methods want to do. So they're creating these averages of gradients as a replacement for having to calculate the Hessian. That still, it's more, it's heavier than, say, Adam.
Again, quickly, at the beginning, what RBMs, PGMs used at the beginning?
For the structure, for image tagging, it's a fully visible Boltzmann machine where the nodes correspond to all the words, say, in English that you want to use for your caption. So it's fully connected.